So, what do a car engine, a refrigerator, and the entire universe have in common? Sounds like a trick question, right? Well, it turns out they all play by the exact same set of rules. In this explainer, we're going to break down those rules, the fundamental laws of thermodynamics.
Let's kick things off with something we're all familiar with, a car engine. Doesn't matter if it's petrol or diesel, its whole job is to take the heat from burning fuel and turn it into motion. But how? How does that incredible transformation from just heat into useful work actually happen? To really get to the bottom of it, we need to talk about the concept that's at the heart of pretty much every engine, the heat engine. Now, this isn't just one specific machine. It's the model that explains how everything from old steam trains to modern power plants get their job done. Okay, so at its core, any heat engine, no matter how complex, has three essential parts. First, you've got a working substance. Think of it as the hot gas from burning fuel or steam that expands to do the work. It gets all its energy by pulling heat from a hot reservoir, a high temperature source. And finally, and this is super important, it has to dump some of that heat into a cold reservoir, which is usually just the cooler air around the engine.
Now, this whole process isn't just random. It's governed by a really strict set of rules. And the first one? It's all about conservation. You can honestly think of it as the universe's most fundamental accounting rule.
And here it is, the first law of thermodynamics. You've probably heard this before, right? Energy can't just be created out of thin air, and it can't be destroyed. It just changes form. It transforms, say from the chemical energy locked in fuel into the heat that actually drives the engine. To really get this, we have to talk about something called internal energy, which we just call U. All you have to do is picture it as the total energy humming away inside a system. It's all the kinetic and potential energy of its molecules, all that jiggling and buzzing, all added up. And what's really cool is that you can express this law with a beautifully simple equation. The heat you add to a system, we call that delta Q. It has to go somewhere, right? Well, part of it is used to increase the system's internal energy. That's our delta U, which basically makes its molecules move faster. The rest of it gets used by the system to perform work. That's delta W, like, say, pushing a piston. That's a great, simple way to put it. The energy you start with is always perfectly accounted for. Here's another way to picture it. Imagine you're heating a pot of water with the lid on it. The heat you're adding, that's your delta Q. It's doing two things at once. First, it's raising the temperature of the water, which is the increase in its internal energy, the delta U. And second, as that water turns to steam, it expands and pushes the lid up. And that, right there, is the work being done, the delta W. See? The energy you put in is perfectly accounted for. It's just been split between two different jobs. Okay, so the first law tells us energy is always conserved. It never just vanishes. And that brings up a really big question. If no energy is ever truly lost, why can't we build an engine that converts all of its heat into useful work? I mean, seriously, if no energy is destroyed, shouldn't we be able to design a perfect engine, one that takes every single bit of heat and turns it into motion? To answer that, we have to talk about efficiency. And in simple terms, efficiency is really just a measure of how much bang you get for your buck. We figure it out by taking the useful work we get out of the engine and dividing it by the total heat energy we had to put in from the start. But here's the reality check. In any real-world engine, a huge slice of that initial energy is always lost to the surroundings. It just radiates away. It doesn't get converted into the useful work we actually want. We call this waste heat. And that leads us to a truth you just can't get around. For an engine to be 100% efficient, the amount of heat lost to the surroundings, that waste heat, which we call Q2, would have to be zero. And in the real world, well, that's just impossible. And look, this isn't because our engineering isn't good enough yet. It's a fundamental law of nature. The second law of thermodynamics, specifically in what's known as the Kelvin-Planck statement, makes it official. It is impossible for any device to have as its only result the complete conversion of heat into work. There will always be some waste. You just can't get around it. So, we've got the rules for engines, but what happens if we run the whole process backwards? Well, it turns out that's exactly how the refrigerator in your kitchen works. This table really lays it all out. A heat engine follows the natural flow of things. Heat moves from a hot place to a cold place, and in the process, the engine does work for us. A refrigerator does the exact opposite. We have to do work on it by plugging it into the wall to force heat to move against its natural direction, pulling it from the cold space inside to the warmer room outside.
For fridges, we don't really talk about efficiency. Instead, we use something called the coefficient of performance. This basically tells us how good the fridge is at its job, how much heat it can pull out for every bit of work we put in. And just like the second law says an engine can't be perfect, it also means a fridge can't work for free. You always have to put in some work to make that heat move where it doesn't want to go.
So this is where it all comes together, because these aren't just engineering principles for building better machines. These are the fundamental laws that govern energy and order across the entire universe.
So if you take away just two things, let it be these. The first law is the universe's rule of conservation. You can't get something for nothing. And the second law is the rule of inevitable loss. You can't even break even. Every single time energy changes form, some of its quality is lost, degrading into unusable waste heat.
And this leads us to one last really profound idea. Think about it. Some things in physics, in theory, could run backwards just as easily as they run forwards. But in the real world, almost everything is irreversible. You can't unbreak an egg, right? The second law explains why. Real processes always create waste heat and disorder, making them a one-way street. And this one-way flow of energy, it might just be the physical reason we experience time itself as a one-way arrow, moving always from a past we remember to a future we can't.